I would like to welcome you all. Thank you so much for coming to this panel. I'm excited to be at a place that's talking about commercialization of fusion. It's an area that I think a lot of people are like, whoa, why are we even starting to talk about that yet? And I hope what we'll cover tonight is why that's a conversation that is interesting to be having. But first, because I wasn't really sure what the backgrounds of people were going to be, I'm going to talk a little bit about what fusion is and that there are a variety of ways to do fusion. And in fact, each of the technologies here today have different approaches for how to make fusion happen. So what I'm really aiming to do is set the context a little bit. So most of the work that I do is in fission, where you take a heavy atom that's relatively unstable and you split it into two pieces and you get energy out of that. In fusion, you do the opposite thing. You take two light atoms and you fuse them together into a new larger atom and you get energy. And which things you fuse together and what you get out of it varies, and how difficult it is to do varies by which things you're combining at which pressures and densities. So the thing that most people use is DT fusion. So this is when you take, here we go. You take deuterium, which is a hydrogen atom with an extra neutron, and tritium with a hydrogen atom with two extra neutrons, and you mush them together, and then you get helium and another neutron that has quite a bit of energy and some energy. Helium-3 is another way to do this, and then you get protons out and you don't get any neutrons. So there are different things you can fuse together. Why do we care about that? And I have one more, maybe two more slides with like sciencey things, and then there'll be less sciencey things, and then we'll get back to sciencey things. So these plots partly are to illustrate that it's super complicated and there's a lot going on. But there are the things that we really think about inside of fusion are what temperatures things are happening, what pressures, and the pressure determines like what is the density of the material. And so those things govern how easy a fusion reaction is and how much energy can come out and how quickly it happens. So this plot is the density of the nuclei, and this is the energy. And when we say energy, that frequently translates to temperature. So when you're looking at, this is in kilo-electron volts. 1 electron volts is almost 1200 Kelvin. So this is like very high temperatures. And so you need very high densities or very high temperatures. And sometimes there's this like sweet spot in the middle where maybe you can get away with a lower density and a lower temperature, and that might be an easier thing to think about. And we'll talk briefly about the kinds of machines that are more traditional that people have been researching and what they're shooting for. But this is DT fusion, deuterium, tritium. You can see that you can maybe use lower density and lower temperatures. So a lot of people work on that because you can do lower densities and lower temperatures. Those are easier things to make in reality. There's deuterium-deuterium fusion. There's deuterium-helium-3. There's proton and boron. Helium-3, which is the hardest one because you need the highest temperatures and the highest densities. This is the likelihood of interactions to happen. So this is how easy it is to make fusion to happen as a function of energy. And so again, you can see DT is the most likely, helium-3 is the least likely, and there's sort of this spectrum in between. So the point of all this is you can have these different reactions, and how hard they are to make happen requires different temperatures and densities, but getting something to be, so this is like nuclei per meter cubed. Getting something to be 10 to the 30 nuclei per meters cubed is a challenge, or getting something up to 100 kilo-electron volts of temperature is really hard. So these are like very extreme situations, which is what makes fusion sort of awesome and interesting. And I stole this from General Fusion, so you're going to see a version of this that renders better because my Mac broke yesterday, so I had to make this in LibreOffice. Sorry. Linux backup plan. So when you're thinking about this version of, and actually, this must not be the, I had saved this as a PDF where the words were slightly more visible. But okay, so this machine, this magnetic confinement, this is like, how many of you have heard of ITER? Okay, so ITER is this giant machine that they're building in France. I'll talk a little bit more about it. but it's magnetic fusion, and that's really working on all confinement. And then we have inertial confinement fusion. Have people heard of the National Ignition Facility, or NIF? Okay, that's this one. And so you take a bunch of lasers and you make the, so in ITER you really focus on getting the temperature very high, and in NIF you really focus on getting the density very high. So you take this material and you compress it. So you're like trading off on this temperature density axis. And I'm going to plug APRA-E's program. So APRA-E actually has a fusion program called Alpha. And they're looking at how do you find this like middle space where you can get a lower temperature and density combo, and looking at what might be possible there. And so that's a little bit in the direction of what some of what general fusion is doing, is how do you have this balanced sort of space. So there's this spectrum of fusion technologies. Some of them really focus on temperature, some of them really focus on density, and some of them are looking at a space in between. And also the companies up here are fusing different things together. So there's a lot of different ways to look at fusion. And why is it that we think it seems weird to be having a panel about commercializing fusion? Well, fusion's super hard. Why is it hard? Plasma physics, there are a lot of things that we're still learning about. There's a lot of simulation work. There's quite a bit of detail still going into understanding plasma physics. Break even. We are not really yet at a point where we get more energy out of a fusion reaction than we put in, and getting to that space is a challenge. So how do you get break even? How do you get break even consistently? How do you make sure you get enough energy out of a fusion reaction so that you can do this thing, actually convert that energy to electricity? So once we get to break even and we get a larger amount of energy out than we put in, how do we actually capture that energy and engineer a fusion machine? That's a big unresolved question depending on the type of fusion. Again, depending on the type of fusion, if you have these very high temperatures, or if you have these very high densities, you need materials that can withstand pressures or temperatures that can be very high. You notice that the DT fusion had a neutron coming out. Those neutrons are very high energy, and very high energy neutrons totally destroy materials. So you have this like high temperature. So you have high radiation environments inside of fusion machines that can be really difficult for materials. And then there's an operation strategy. So like in the NIF machine, you have a pellet that gets fused with lasers. How do you make sure that you can replace those pellets rapidly and have a repetition rate? There's a lot of operational details inside of fusion that can make it difficult to make machines that are really reliable. So there's a lot of challenges. And inside of that space of these really big challenges, there's really exciting science going on. And there's really exciting science going on in sort of a new paradigm, because there are all these fusion startups now. And that's kind of this new and really quite exciting space. I mean, Tri Alpha has been around for a long time, but there are other companies that are joining this. Like 10 years ago, if you had said there were going to be more than like 3 fusion startup companies, I would have been like, what are you talking about? But it's quite interesting. So this picture is ITER being constructed in the south of France, and this picture is NIF. And what you might notice is that they're very large. These are very large, very expensive, very long time frame machines. ITER is like a $20 billion, 20-year construction project. And those can be really untenable for doing science rapidly and innovating rapidly in a space that has so many hard problems to solve. So what's interesting about the fusion startups is that they're taking sort of an innovative, fast failure, quick learning approach to these very hard problems in a way that I think is allowing for more rapid advancement of science, or a different sort of scale of advancement of science. And that is, to me, what's the most exciting about it. And there are many different ideas that people are investigating, and they're able to investigate them more rapidly and more thoroughly, because they're not these $20 billion, 20-year projects before you get your first bit of science out of them. They're doing things much more creatively. And there are new funding sources in the space. Instead of it only being a thing that large governments can fund, which has historically been a lot of the fusion work, venture capitalists are starting to fund fusion. There are semi-philanthropic investors who are funding fusion. APRA-E has a fusion program. So there are a lot of different pots of money that, again, like 10 years ago, if you had said VCs are investing in fusion in some real way, I would have been like, what? So it is really, I think, an exciting time, and I think there's a lot of interesting potential, and that's what we're going to hear about today. And
over to me.
Over to you.
So
we just go down the road.
Push on this bar? Oh, yeah. All right, I'm Michel Laberge. I'm the founder and chief scientific at General Fusion. General Fusion is in Canada. It's a small company with about 75 people. We started in 2002, so it's already 15 years. 15 years, shit, that's a long time. That's a little slower than I wanted when I started that, but anyway. So we raised about $100 million so far, about 20 million from the Canadian government in grant, and maybe 80 to 100 million of private money, like VCs and stuff like that, so we're doing okay. I did my PhD in fusion. I was doing laser fusion, one of the techniques that Rachel just quoted. And then after that, I went and did some laser printer in the industry, nothing related to fusion. But after a while, I noticed that the energy situation on this planet is a bit of a bind, like global warming, pollution, blah, blah, blah. So I say, okay, I know about fusion. Fusion is the solution. Maybe I should do fusion. So I could join the big lab, like the NIF and the ITER. But I look at those guys, and they're moving a little too slow, you know. They're big, they're slow. It's not an happening thing. However, they've been working at it for 50 years, and they're very near. Like ITER will likely work. They just scale up from other machines that were almost there, and they're scaling up a bit. NIF, they're a little short on the laser power, but if you give them a couple of more megajoule for a couple of more $1 billion, it would probably work. So I think humanity knows how to make fusion now. Both the laser fusion and the magnetic fusion, give them enough billion, make another big machine, and it'll work. We know it. We know that fusion is doable now. It took 50 years to learn that, but we know it. However, it's too big, and to make that into a reservable power plant that will make electricity at a real cost, I personally don't think that's going to happen. So it's now time for the private industry to come in. We're almost there. What we need to do is to make it a little bit cheaper, a little faster. So I decided I'm going to start a private fusion company, which is totally insane. My wife threw a fit. She says, what? You're leaving your big, well-paid job doing laser printer or doing fusion? Well, fusion is more fun than laser printer. So I think, what the hell? We'll do that. At least, if it doesn't work, at least we'll have fun. Anyway, so I started this company, and it grew and find some money and everything. So I'll give you a little spiel now about what it is we want to build. So this view graph here appeared that Rachel stole it to me, so it took a bit of air out of my talk. So on the left there is the magnetic fusion. So this is the big tokamak. They hold the plasma with a magnetic field. The magnetic field prevents the heat from escaping, but the heat still escapes quite a bit. So their technique to make it work longer is to make it bigger, because you know it takes longer for a big rock to cool down than a little rock. So if you make a big tokamak, it'll take longer for the heat to escape, and as it'll cool down slower, it'll make more energy, so they're making bigger and bigger. On the right side is the laser fusion dude. Take a little ping pong ball, they put the gas in there, they put a whole bunch of laser, they squash it. They squash the ping pong ball really, really quick, in 1 nanosecond, 1 billionth of a second. And when you squeeze something very fast, it gets hotter. And now there's no magnetic field to prevent the heat from escaping, so the heat can escape very fast, but they squash faster than that. Except the laser costs billions of dollars because it's a big complicated thing. So we want to be in the middle, something called magnetized target fusion. So we do a magnetic field, so we have magnetic field to prevent the heat from escaping, and we squash it. So it's a bit of a mix of the two. So we do a magnetic field that holds the heat there a little bit longer, and we squash it. And because it's a magnetic field, we can squash it smaller. So in place of squashing it with expensive laser, we want to squish it with cheap piston. Basically, we want to make a sphere full of jackhammer and squash it with compressed air. Something quite simple and inexpensive. So it's going to work a bit like, oh, no, one steel here. So about money. So on the left side is ITER, which is a very, very big machine, which run at a fairly low density. At the bottom of the graph there is the density of the particle in the machine in particle per centimeter square, centimeter cube, sorry. So the one on the left is ITER that runs about 10 to the 13 parts per centimeter cube. The air that you breathe here is 10 to the 19 parts per centimeter cube. So in ITER is 1 million times less dense than the air here. And the laser guy on the other side is at 10 to the 25 parts per centimeter cube. This table here is 10 to the 22. So it's 1,000 times more dense than the table. So they want to cruise this extremely high density by squashing. Well, it's very nice, but the big machine at ITER costs a lot of money because it needs a lot of energy in the plasma. The machine on the right costs a lot of money because it needs a very powerful laser to squash it so fast. We think it's going to be a heck of a lot cheaper in the middle, so we want to operate in the center. So this is what we want to do. It's a big ball. So there's a grid in the center that spins. I don't know, the machine will show the grid, and that pushes the liquid metal outside. So it's a big pile full with liquid metal. The grid spins, jam the liquid metal on the outside. Then we inject a magnetized plasma. We form that with some equipment on the top there. This big ball that goes in the center, that's the plasma. Plasma is a hot gas with magnetic field. And then after that, we fire all those pistons, and the pistons shove some liquid inside and squash the thing. So when you squash the thing, it gets hotter. We'll achieve fusion condition. The neutron comes in. And as Rachel said, neutrons are a very pesky thing. When they hit metal, they break it. So a lot of fusion machines don't want to do DT because the neutrons are going to damage the machine. But DT is the easiest fusion to do. So we want to do DT. We think that doing the fusion easy first, it's like you should learn to walk before you start to run or something. So we think the DT is a better idea. However, when at maximum compression, it's all surrounded by liquid metal. So those pesky neutrons, they will hit the liquid metal. You can't break liquid metal. It's not like a piece of metal. So it's impossible to break it. It'll absorb all the energy from the neutron, and we won't break the metal, which is great. The metal will heat. We will pump this hot metal outside, put that in a heat exchanger, bubble some steam. The steam will run the turbine that makes some electricity, and some of the steam will turn around and run those pistons. So this is going to be like a spunky steam engine, essentially. And people laugh at us. They say, wow, it's so 19th century. But it's cheap. Like steam machine, piston, ring, this is cheap. Superconducting magnet, big laser, this is expensive. So in my opinion, it has to be cheap. I tell all my engineers, if you can't get it from Home Depot, it doesn't go in my machine. Like, people like to put all sort of exotic things because they love technology, but it costs more money. At the end of the day, this has to be cheap. So this is what we want to build. So what are we doing so far? So on the left there, we're working on a plasma injector. This machine that put the plasma in. So we're building various plasma injector. We're trying to make the plasma at the beginning before we squash it to look good. In the middle there, we're working with liquid metal. We're trying to compress this liquid metal. It has to behave properly. And on the right side there, we actually do some plasma compression. Because we don't have this big machine with pistons, so to date, we compress it with high explosive, actually. With this tank that you see on the bottom right there, we wrap high explosive around that. We implode it with explosive, and then we can compress our plasma. We do that as a substitute to the big piston machine because we haven't got enough money to build a big piston machine. But all those bits now are starting to work pretty good. So we would like to build this big machine here. This is the full, including the plasma and the big piston and the rotating liquid metal. Only problem is it costs $300 million to build that machine. So right now I'm going around the planet with my hat for $300 million. And I'm flying after this meeting to go to England to deal with that. And this is what we want to build. And then if that works okay, then the next mission after that will be to make some real power plant out of it. Thank you very much.
All right, so I'm Matt Thompson. I'm Director of Physics at Tae Technologies. We recently rebranded from Tri Alpha Energy, which some of you may have previously known us as. I'm going to turn a little bit here so I don't get too big of a crick in my neck. But at TAE, when we looked at the problem of fusion energy, we really wanted to start with the end in mind. And from our point of view, the end is a commercial power plant. And scientific validation of being able to fuse, as you heard, is probably coming soon through ITER or NIF. But that is a necessary but insufficient condition. Because if you're a power-producing utility, you care an awful lot about other factors as well. You care a lot about whether the unit size of the power plant is reasonable. Can I afford it? Will it take a reasonable amount of time to build? And you also care a great deal about whether or not you're going to be able to maintain it, whether you can build it with materials that are relatively easily available, not super specialized materials. And I'm going to explain this aneutronic fuel bullet in a second here, but you would really, really like it if you didn't have to deal with a lot of radioactivity, especially radioactive materials. So looking at all this, as Rachel talked about, a lot of this is fuel cycle dependent. So TA's vision is to make a run directly at what's called an advanced fuel cycle. For us, it's protons and boron-11. And if you can burn this fuel, your inputs are not radioactive. Boron is a light element. There's lots of it around. It's not radioactive. Your outputs are not radioactive. You just get 3 helium atoms, and you get a copious amount of energy. So essentially, you're getting the benefits of nuclear power without radioactivity, essentially. The machine will generate X-rays while it's operating. It might activate a little bit while you're running it. That means the structure gets a little bit radioactive, but there's no waste in the fuel stream. And also, there's reserves of this all over the world, so there's not going to be a Saudi Arabia of boron, for example. Now this comes at an enormous cost. Well, not an enormous cost, but by flipping the script and going to an advanced fuel that will take out a lot of the engineering problems of dealing with a lot of high-energy neutrons, take out the problem of breeding or creating tritium. You take out that backside engineering risk, but you give yourself a harder science problem. And the harder science problem is that this fuel burns at about 10 times, a little over 10 times the temperature of deuterium tritium. And so we went to look at systems that might give us a pathway to making a thermos bottle that good. Best thermos bottle ever created on Earth. These temperatures we're talking about are actually hotter than the center of the sun, by the way, which gives you kind of a feel. And you can't confine that in a material object. It will vaporize it. So what you end up doing is trying to build a better and better magnetic bottle. And so what we're looking at is what's called a field reverse configuration driven by particle accelerator beams. And the fluid analogy to this is like a smoke ring, if you can have that picture in your head. So inside sort of a straight solenoid magnet that we all learned about in introductory E&M, you have a plasma that then is confined. It's made into closed field lines in a closed magnetic bottle by currents within the plasma itself. So there's kind of a virtual solenoid magnet operating within the plasma. And the theory tells us that this has the prospect to scale very favorably. The ability of the plasma to retain its energy in particles scales very well with temperature, which is why we think it may be a suitable candidate to do an advanced fuel reaction. So to give you a sense, I've got a little animation. And what our machine does is it makes 2 of these smoke rings of plasma. It launches them at each other. They merge in the middle, and then we hit it with these accelerated particle beams to both drive the internal current, add energy, and add particles and current. So that's the animation we're going to look at right now. So here we're forming the 2. We launch them together. They meet in the middle. And these yellow things on top are the particle accelerators. And here's the cartoon picture of the beam launching in and driving the plasma. And to give you a sense of where we are as a company, I've got the sort of the company highlight reel. Tri Alpha Energy, now Tae Technologies, has existed since about 1998. And we got a very classic startup start, almost literally a few guys in a garage back in 2000. And you'll see that we've advanced pretty rapidly through levels of technology, from something very basic to something a little more sophisticated. By 2007, we were doing full-size national laboratory scale experiments where we demonstrated that we could stabilize FRCs, that we could sustain FRCs. And what you're seeing right now is the construction of our current machine. And if you missed it, we were pouring concrete in October 2016, and we started operating in May 2017. And that is one of the things we really think we bring as value as a private player in this, is the speed at which we can move. And this is a little montage of the construction, an overview of the machine as it exists now. And this is, we made plasma in this today on our path to our next milestone, which is heating up the plasma and checking how good the thermos bottle is as we go to higher temperature. So we are TAE, and we thank you for your time and attention.
Good evening, and my name is Tom McGuire, and and I lead the Lockheed Martin Aeronautics Compact Fusion Reactor program. And we're a newer player. We've been at this maybe just a few years. We're about 25 people, and we're based in the desert north of Los Angeles, in Palmdale, California. And Lockheed is a pretty large defense contractor. Not what you normally think of as an energy company, but we really got into this looking at how do you improve and move the needle for energy for some particular in the aeronautics company. We really like airplanes. So if you want to make the next generation airplane fly 10% farther or 10% more efficiently, that's really hard to do with normal fuels. And so we basically opened up the aperture. It's like, okay, well, what's a better fuel? And you look at nuclear, and then we honed in on what is more likely we can actually make something fly around. So we probably picked the hardest application to apply fusion to, but that's how we got our start. And what really started the program off beyond that initial kick was we're a security company. And you think about what drives security issues around the world. Resource scarcity is a huge problem. And on top of that, you have the issues with climate change. And so as an energy issue, it's an issue for our government customers and for the world at large. So that's really why we're doing what we're doing. And in brief, our concept is an experimental program, and we're trying out an idea that is a magnetic confinement, our version of a sun in a box, that we think has a higher promise of being able to be developed rapidly at a small scale, that we can do iterations on a year-long cycle, and 3 to 4 cycles away from reaching that break-even experiment. So what you see on the left is a conceptual design of what a linear ring cusp reactor, which is the technology we're developing. The scale of our lab, we're quite a bit smaller, and that's going to get bigger with each experiment. At the end will be something closer to what you just saw from TAE. And on the left, or the right, is a picture of the current experiment showing the cusp plasma. And the concept, our big idea, is that we can make a plasma that's much more stable than some of what has been done previously. And that's what we're seeking to show experimentally. And if we can do that, we can enable a concept that's really compact. If you can use all of the magnetic field energy so that it's in perfect balance, magnetic field pushing on the plasma, and that it's equal. That's the way plasmas behave out in the cosmos. If you look out in telescopes and you look at plasma structures, that's what you see. The challenge on that is reproducing something that's that stable in the laboratory so that the plasma can self-organize and relax down to that state. And that's what we're trying to show, that we can actually achieve that in the lab. If you can do that, you can generate a plasma that is small. So you can see the dimension on there, something in the order of tens of meters. So a reactor that could fit in the size of this room. That's the vision. That's why we're interested and think we can make progress in a fast cycle. It works much the same as you've heard already. We energize a plasma. We get it up to those 200 million degrees hotter than the sun temperatures. It generates neutrons. The first reaction that will be accessible is deuterium-tritium. If we can build the engineering systems around that, we'll run with that. If those are untenable, we'll keep pushing ahead. We have options. But the first one will be deuterium-tritium, and you make neutrons, and how you harness that heat, you have a blanket shown here in the gray. How big that blanket is to capture those neutrons dictates how heavy it is, and how heavy it is really dictates a lot of the cost, and also how crazy you can get with the applications. Airplane is pretty darn hard. we fly some very heavy airplanes, but that might be one of the most challenging applications we can tackle. Modular power plants, so you see in the upper right, is probably a more realistic first application. But so that range, 200 to 1,000 metric tons, that is a lot smaller in terms of mass. That gives you a range of something you can deliver and make in a factory, deliver and build as a type of architecture. And just to close off, the main physics concept of what sets us apart is that we're trying to hold the plasma in a stable fashion where the concept is stable and that the plasma is pushing against the magnetic field. And if that works, what we'll get is something in the where you get to the plasma that's like in the bottom right, where instead of having a magnetic field that holds every particle in place, you're only holding it on the edge. So the equivalent is that if I wanted to keep everyone here confined in their seat, I could tell you to stay in your seat. I could try to put a magnet under each of you, but everyone starts jostling and you start getting hungry and everyone starts moving towards the doors. It's a lot easier just to put people along the doors and just keep push back. It's like a mosh pit. So we have the mosh pit approach. And really seeing whether that can be made to be stable in the environment. And that's what we're trying to do. We're spending most of our energy on experiments as where we can make the most headway quickest. And the whole strategy is to take the biggest risks. And the biggest risk with confined fusion, nuclear fusion for power, is understanding the plasma confinement. We tackle that, and then we'll make more. Then we'll branch out and add materials, operations, how to make a manufacturing plant, where you can send them, a lot of the details that go into the applications. Is it safe to fly airplanes? What kind of ships can you put it on? Those questions will come later. So that's a general overview of what we're trying to do. I will pass the mic.
Okay, great, thank you. Well, good evening, everyone. My name is Ray Rothrock. It's amazing to see so many people here interested in nuclear fusion. My life started out, I fell in love with nuclear energy when I got the Atomic Energy Merit Badge when I was 13 years old for my Eagle. And it's only gotten bigger and better. I don't know why I'm sitting here. I feel like I'm the Howard Wolowitz of the Sheldon Coopers here at some level, because I don't have a PhD in nuclear anything. But I was a nuclear engineer, worked at Yankee Road back in the 70s. I was actually in the plant when 3 Mile Island happened elsewhere. And then I moved to the Silicon Valley in 1981. And after some time, I became a venture capitalist. And I joined the Rockefeller family in New York City, where we had a mission to invest in things that would change the world and make it better, and help people. And it wasn't about IRR, it wasn't about doing things fast, it was about doing things big and fun. And so with that mission, along the way, you might remember in the 2000 time frame, this whole climate change thing happened. And a lot of VCs, in our firm included, we decided to stand up an energy group. So I led that energy group. And we made 12 energy investments. One of those was Tri Alpha. And so I don't want to get into the Tri Alpha. I'm happy to answer any questions about it. But let me just give you a sense of VC life in this sense. Because when I transitioned out of Venrock, I retired in 2013 with Ross and some others. We made a movie called Pandora's Promise. Everybody seen Pandora's Promise? If you've not, it's on Netflix. Download it, look at it. 90-minute documentary. But it began an advocacy role. And so I spent the last 3 or 4 years in Washington, on my knees, begging the secretaries of energy to do things differently. And one of the things that Secretary Moniz did was create this GAIN program. But, in the cliche, be careful what you ask for, he put me on the GAIN Advisory Committee. GAIN stands for the Gateway for Advances in Nuclear Energy. So we started a small program, DOE started a small program, because one of the things we discovered when we did Pandora's Promise, there were about 50 nuclear startups out there. It just keeps getting bigger and bigger. We partnered with a group in Washington to help us do this research, but when we put that in front of the secretary, they were amazed. No one believed us, in fact. No one believed us. And I remember Secretary Moniz said, Ray, I've known Ernie a long time. I'm an MIT guy. He said, I don't believe you. He says, put some of these investors on the telephone. So I organized, he wanted to have him come to Washington. I sort of laughed at that. I said, but I can get them on the phone. So I got them on the phone. And I said, yeah, we're interested in nuclear energy, and we're putting our money to work. And this is, George Soros and Stan Druckenmiller and Art Sandberg. I mean, these are big names out of New York. They're just blown away. So suddenly the department is all about innovation. And one of the things I take some credit for, Ross takes some credit for, was the Silicon Valley does things differently. We innovate 2 principles: many shots on goal and speed. Those 2 things are the driving principles of innovation in Silicon Valley. It's been that way since I moved here in 1981. Do things fast, lots of competitors, bring it on. That's what gets the problem solved quickly. And nuclear today, in the last 5 years, it is a blooming field of probably well more than 50 companies. Here's just a sample of a few. So let's go get it. This thing called ITER, I always thought that said ITER money, but it strikes me it's just this massive project. And the last thing I'll say is a venture capitalist. So I wrote a paper 3 years ago. The National Academy published it. It's in the Issues in Climate magazine, January 16, I think. It was about what is the value of venture capital? What's the value? What role do we play in innovation? Ideas come out of universities. Government funds research labs. We have the best national labs in the galaxy. What's our role? First of all, we provide the cash. That matters. And because it's our cash, we can help direct and stay focused. And I will say, in the benefit of Tri Alpha, they've come to us many times and seen something in physics, some little shiny object they want to chase. And the board would say, no, you're on fusion. And they'd go chase another one. No, you're on fusion. And that focus is what makes it possible to build a machine in 7 months. Burt Richter, famous Burt Richter of Stanford, it took 11 months to build the machine I initially invested in. He went out and put his hand on the slab and said, you'll never have anything in 3 years. 11 months later, we were squirting plasma. So the focus, the money, the talent, the ideas, we have to make all of that go. I don't know who's going to win, but somebody is going to win and it'll change the planet. And that's what I think my job is. Thanks. I just want to say, I don't think anybody watches The Big Bang Theory. There's only a couple of laughs about that.
It hits a little close to home.
That's right.
Sorry. Anyway, thank you.
So I'm going to start off and ask a couple of questions to the panelists, and then we'll open it up to audience questions. But I think I actually really liked Ray's comment about staying focused. And as people who are scientists inside of companies trying to get things done, but sort of, I think, at heart, you all are scientists, how do you manage inside of your company, keeping your company really on focus with that when there are all these polls to go investigate these things? So I'll start in reverse order. So what do you do to keep that drive? Like, do you have your board yell at you, or do you have Lockheed yell at you, or like, how do you do that also for your team?
I think that's a hard challenge that we fight with every day, because we are definitely susceptible to shiny object syndrome. And I think there's a collective excitement into what we're doing, and there's also a motivation. No one wants, and I don't say no one, we don't want to do the same thing for 20 years. We really want to make progress. And I think that motivation as a team to meet our milestones sort of keeps everybody in check. But it's tough when there's a new technique, a new diagnostic. And our philosophy is we want to minimize the amount of miracles needed to get to the end of the chalkboard. And there's other folks that are spending time to develop things, and we want to leverage as much as we can. So I think it's the group dynamic really is as opposed to an outside person saying you must do this.
Yeah, well, it definitely is a challenge. I mean, those of us who have come through a scientific development, you're focused on novelty, you're focused on discovering new things. If you find some esoteric plasma instability, you really want to study it and publish a physical review letter. So the counterweight to that is collecting a team that's really focused, again, on the end, focused on the product, focused on results. I won't lie, I get to be the bad guy a lot, right? To say, no, we can't do this because that's not addressing the core problem we have right now. But progress motivates people. You know, when you, in a year, you build a device that they know would take 3, 4, 5 times as long if they were at a different program, people get on board. And that takes care of a lot of the motivation for us, I think.
Well, at General Fusion, I'm very focused. I decided I'm going to save this planet by making fusion happen. So this is why I started the company for, and that's what I push for. And interestingly, our board would rather take, well, would not rather, but say, what if this fusion doesn't work? What are we going to get? So some of the board are proposing to make spin-off of some technology. You're a bit guilty of that, by the way. Those guys are doing medical stuff too.
It's not my money. It's okay.
They're trying to make medical spin-off. But so a few on my board and actually some in my company would like to make spin-off. Hey, we got this nice diagnostic. We could sell that to those guys over there or something. Yeah, we could do that. Makes a little money, which is nice, but it will defocus it from making the fusion machine happen. So I'm refusing to do that, and I'm fighting battle with the board and with some other people in my company. No, I don't want to sell little gizmo. This is not what I want to do. I want to make energy to save the planet. And selling gizmo is great. It makes a little bit of income that would make the company, afloat a bit longer. But this is such a distraction. I say it's not. We're making fusion here. And one of those days I might lose, by the way. But so far I'm winning.
So I have one deeply personally motivated questions. So I do computational work. So you're all doing experiments. What is the balance between computation and experiment, and how do those feed into one another, and how do you strike that balance? And we'll start with Matt and go this way.
All right. So our computational friends, and we have a substantial group, and we have multiple in-house codes that we've written to look at this stuff. And in a lot of ways, they're our scouts. They're the ones that are out there in the front gaming sort of the situations that would make sense for us to pursue. In this machine we just built, we heavily modeled. We added a new component between the formation section and the main confinement. We wanted to make sure that that wouldn't cause any problems. They modeled it up for us. We gamed out all the situations. We had a high confidence that it would work. First shot, it worked just fine. So there are scouts out there looking at what comes next, and they also help us a great deal in understanding the data. So data to experiment, back again, I didn't get to show it, but we have a wonderful slide where we made the experimental data in the same color map as the simulation, and you couldn't really tell the difference. You had to label it.
And do you use experimental results to feed back into the software? How?
Absolutely.
Okay.
So we validate with what happened on the experiment, and it's the classic iterative process to refine the codes and the models.
I guess, do either of you have different things to say than that? If not, I'll say something
Oh,
else.
it's pretty similar at General Fusion. I can tell you maybe the amount of resources. I think we have 5 people doing simulation, and we probably have maybe 15 people doing other stuff. So, it's 1/4 of the scientific are actually doing simulation. So that's a fairly large amount of resources. There's also, computer-wise, there's the people that do the simulation, that try to predict how the plasma would behave and all that, and how the machine would be. But we also have diagnostic analysis, like there's some fancy chewing of the data to process various diagnostic. So we probably have 2 guys that write codes for that, just some code in support of the data for analysis of the data. So yeah, there's lots of computing going on there.
Yeah.
Yeah.
The one thing I would add is that we've been experimental for the most part, and just in the last year we really ramped up our numeric efforts, but it's still small compared to the experiment. And the guiding principle was, how do we get the best answer for the amount of resources we have? And picked, okay, if we want to try to answer this question, what will give us the best answer given our current situation, our current state of understanding? So as a little bit being younger along our development cycle, for us that was experiment, which is a giant analog simulation with trillions of variables and degrees of freedom in real life. But then diagnostics are hard. And so that I think it's a constant balance that we keep weighing as we move forward. And it's an important part to balance.
Actually, I want to pile on there. I think there are 3 legs to that stool. There's the experiments, there's the computation, there's the theory. Because when you're in the area of physics that Tri Alpha and all of you are in, it's new physics. There's new things you're learning. You get new answers. You can't answer it. And at least at Tri Alpha, early on, we assembled a science panel, an outside science panel. Not only did they bring just great questions, I mean, that's what brilliant minds really do, is ask the best questions, but they brought some experience. They said, in fact, I'll tell a little story. We were going to have this simple machine, 1 keV, and then we're going to go right to 200 keV, just one hop. And I said, nah, that's probably not a good idea. You're going to learn a lot, and sure enough, we'll have about 4 steps to get there. But that wisdom of the crowd, if you will, these very brilliant people asking questions, and I will say we had to go out and raise more money because they wanted more diagnostics, but it wasn't for just academic reasons. It was like, you need to understand this, you need to understand that. And these were questions that we had not asked ourselves. And the due diligence, it took me 6 months to do due diligence on this project. So I learned a lot about those questions. So I'd say it's the theory, the computation, and the experiment.
So my next question is, you brought up scientific advisory board. What is the balance of outside input for companies that they're not national labs, where you're used to having sort of this top-down decision-making directive, but getting outside perspectives from business, finance, and science? How do you balance that? And from sort of the VC perspective, and then from inside, I'm curious.
Yeah. So in the case of these deals, I'm in another nuclear deal, Transatomic. It's very science-oriented right now. So we want the best scientists we can get around the table. We have a few Nobel laureates, a few Maxwell Prize winners. And it's all about that. It's about the electromagnetism, just everything, the particle physics. And in fact, we've had a few of the science panel move on because it's progressed. The sort of fundamental physics that we were learning 5 years ago, we've learned. They go, I don't have any more to add. So now we're bringing on people that have a little bit more engineering, maybe, a little bit more material science, maybe. Things. So it's sort of evolving over time. And in terms of the business, we just hired a business officer who is all about the economics. If you don't know, the first approximation of the cost of a power plant is the amount of copper, steel, and cement. That's your first approximation. So if it's going to be as big as a gymnasium, that's a lot of copper, steel, and cement. Look at ITER. So you need to think about that. That's just, but you come at it from that perspective, that begins to be a member of the conversation, because economics at the end of the day is what it's all about.
And how do you all, you could just go in whatever order you want, think about the advice that you want and the input that you want?
We also have a scientific advisory board, so we have a bunch of scientific people. In that board, we also have like industry people in the power business to help us deciding a bit on the more sort of business sort of decision. So we have a bit of a mixture between science and business over there, and they're quite useful, those guys. They have lots of experience in what they've done. And you ring them up from time to time, what do we do here? And the guy gives it a good, and we have a meeting. So we get a bit of the wisdom of those experienced guys to help us out. So that'd be useful. And
the balance between science and economics is?
75% science, 25% economics. Okay. It might change later, but we still need AV on science at that point.
So just to add, I think we learned. We've had a couple outside expert advisory boards. A little bit different that we don't have a long-standing one. We convene it when we're ready to do another step and sort of revisit. And it's valuable. It just brings some perspectives that you wouldn't otherwise have. And I found it to be pretty valuable to bring in if we were going to stand up and say, okay, well, we're going to do it better than these guys. Actually get somebody from those guys and come over and get their perspective on what works and what doesn't and what are their challenges. So if you think you're doing better than them, it's nice to get that inside perspective. And then some surprises happen out. One of the most surprising, we're doing this small, and small is better, and like it makes sense from like, well, one was like, well, if you do it too small, it's hard to figure out what's going on in there. So there's a minimum size where you can actually diagnose what's going on. And that was extremely valuable, and that really helped in the initial stage. And then the last one, which I did not appreciate when we started the project, was what's the management load? How are you going to run this project? And getting a little bit of realism early on and ideas on how to do that was really valuable.
Nice. So fusion sort of has this stereotype of the time constant of fusion is it's always 50 years away. So when when you're talking to investors and when you're thinking about hiring, those sort of two ends of the spectrum, how do you talk to investors in a way that you get them to see why they, what do you say to get them to give you money? And when you're thinking about hiring people, how do you get people who are sort of bought into the mission in a way that has the tenacity to want to operate on these kinds of moving the time scale from a fusion constant of 50 to like, what if we could do this next week? Like, how do you...
Not next week.
Well, but
sorry, we want to go fast, but not
how
that
do you
fast.
how do you hire for that?
Okay, first question about what do we pitch. You can't pitch too long a time constant because it's hard to get money for a very long time constant. So we pitch 6 or 7 years. Now we know that we're not going to sell power plant in 6 or 7 years. So what we pitch is that we will evolve the technology to a point that is valuable enough to sell it to somebody else. So the guy will get his money back in 6, 7 years, but we ain't going to sell power plant in 6, 7 years. It's a bit like in the medical, for example. People develop drugs. It's a very long process. So it's actually well established. There's the first investor out there for 4 or 5 years, and then they get purchased out by the big drug company, and then they push out, and etc. So we try to sell, 6, 7 year max to the investor because we know they won't give us any money for longer than that. But it is understood between us and the investor that the power plant is going to take longer than that. So we're trying to say that at 6, 7 years we'll have enough progress to sell it to somebody with profit. So that's how we get away with the fact that fusion is a little long. Now on the 50 years, by the way, I like to point out that fracking, they started fracking in 1920. Okay, I repeat that for good measure. The fracking technology that's now over the last 10 years is making billions to everybody. They started in 1920. I do not know the amount of billion that the fuel company has pissed on fracking, but I would say it's probably a very large number. So energy things takes a long time, costs a lot of money, and people say, fusion 50 years. Well, fracking 100. So take that.
That's really encouraging.
No, seriously. And it has been 50 years, yeah, sure. And it's getting better, and we think we can pull it out, in 15 by now or something. So it's getting better. Take some time. Now, for the employees actually not that hard to get because it's such a nice thing to work on. People want to save the planet, wants to work on something important. So employee will come, even if they understand that, in a small company, it's a bit risky, and we might run out of cash and go broke. So they understand it's a risk, but it's more fun than to work in the academia, in my opinion. Like in place of just writing paper, you actually build gears. So they like that, usually. So we're okay with that, right?
Well, we envision sort of the commercialization phase of fusion being 10 or so years out, and moving from sort of an R&D program into the early phases of commercialization. And we feel our rate of progress supports that, and so that's what we talk about. To get to your point of hiring, again, I always try to look for individuals that have sort of an intrinsic motivation. You can teach skills, but you usually cannot teach motivation, initiative, or sort of natural talent. So that's what we always seek, and we always seek people who understand that they're not maybe going to be writing a first authored PRL every year because that's not what we're about. And folks tend to self-select on that pretty well. And as you said, there's not really a shortage. We have a lot of very eager folks wanting to come on board.
Yeah, a lot on the personnel. Like it is a self-selection process. I've observed that as well. But there is a little bit of difficulty. Some of the specialties, for example, pulse power engineering. There's not as many programs as we would like to see producing graduates, and we've had some job requisitions that were open for a while, and it's not from desire from the people we get. It's just not, the pool is maybe not as big as it could be. But I think you can tell in an interview who's itching and ready to go and ready to jump out of their seat, and that's good. And I would the one thing about how we sold internally, we're a private company. We've been funded totally internally, so our pitch is really not external. It's to our set of various leaders across the corporation. And what really seems to resonate is understanding the risk versus our milestones. So we don't have a set time, whether it's 5 years or 10 years. It depends on the application and what and what milestone you're talking about. But we have an idea of the steps we have to take and what it means when we get to each step. So the next step, and we put a number on it. We say, okay, we think we get to this milestone, our probability of eventually getting to the end has increased to this. And trying to understand it in that simple framework seems to be pretty effective.
Just could I jump in on the financing? So some really important points you all made. So a venture capital partnership lasts 10 years. And after 10 years, you either have to liquidate what you own or somehow park it or do something with it. So when we started, we invested in Tri Alpha in 2005. And I actually had to go to our limited partner advisory council to tell them that we're making an investment that's going to last probably 20 years. Just a fact. It's a long ball game. And they said yes. But interestingly, before that, you bring up a good point, Tom, it is all about milestones. So you raise the amount of money to achieve a milestone, raise money to achieve a milestone. And as you step through that, the risk goes down at every milestone. That's the way biopharmaceuticals are financed. The biopharmaceutical industry, about 40 years old, takes about $500, $750 million to bring a drug to market. And the yield is extremely low. So there's billions of dollars go to market a drug and that one gets through. But it's exactly right. And different investors take different risks at different stages of the process. It can take 20, 25 years. That's okay. We know who those people are. And that system of biopharmaceutical investing is very well honed. I mean, it is well known, the amount of capital, who does the deals, and all that is just a perfect thing. I'm hoping someday these long ball energy deals will have a similar cast of characters, if you will. And a new group that's showing up are sovereign wealth funds, right? Norway, $800 billion, the Saudis, $1 trillion. I mean, there's a lot of money out there if you can tell the story. The last thing I'll say is when you get a little longer out there, I've talked to enough investors and you say, well, this is fusion. They go, what's that? And I say, okay, think about this as an option. You've got oil and gas investments. You've got other kinds of energy investments. This is an option. Fusion is an option. Fission is an option. Buy an option. You start talking financial terms to very sophisticated people who aren't scientists, now they pay attention to you. It's just you got to learn the language, and I didn't know it till.
How do you spell that?
Options? All right. Anyway, it's a way.
That's great. All right, so it's time to open it up to the audience. I saw that hand first. So stand up and yell.
Yeah, hi. How big a hole do you have to dig before you start making money? Each one of their 3 times a day.
It's a gigantic hole.
So how much money do you need before you start making money?
I think $2 billion before we get net energy out, probably, reliably. But you got to remember there's first of a kind, and then you get down the learning curve very, very fast. So, at some point we'll need other partners like governments and stuff to step in, but it's probably $1 billion private capital. Maybe go public, raise some public capital.
Now, this is to get to break even. This is not like starting to punch out power plant to put on the grid.
This is first of a kind.
To go from break even to a power plant, that's going to cost another couple of billions there. So it's a lot of money. Yeah. It'll cost $5 billion before an electron goes on the grid.
Ray, you looked at 50 of these different potential ideas, companies, whatever. What's your sense of when we're going to have a pilot or early commercial? You talked about the dollar amount. What's the time horizon? Because like you, 50 years ago I read about this in College of Science as well. Too. Yeah. We've all been like, oh, tomorrow.
Right.
So what's your sense?
And as Peter Thiel, we only got 140 characters, right?
Yeah.
A fusion?
Yes.
So, I don't know. When I'm asked if I'm pressed, I'll say 10 years. We will light those 4 light bulbs on a turbine somewhere. That's what I think. 10 years, I'll still be alive. That's my hope. But I'm encouraged because the science is getting vetted by the world. All of these folks and many others they publish. I mean, it's out there. This is no longer a skunk works and nobody wants to talk about it. Remember, there was a time when, right? Exactly. Skunk? No, good. But now it's out there. And look at the young folks. I mean, tell us about the Berkeley Nuclear Engineering. I mean, people are piling in here like crazy because there's a taste that it's going to work. There's a taste we're on a path. Any one of these could work. That's very exciting. So I think we're probably 10 years out.
If you guys can talk about what's going on in China in this field.
It's 8 years out. Yeah. Competition's a big deal.
Yeah. Well, Chinese is actually probably the country that is putting the most resources on fusion right now. Yeah. They're part of the ITER. They actually totally pissed how slow the ITER is going. Like, they look at this big multinational, and I was at the conference just this summer, and the guy was showing the progress for the machine after ITER, the Chinese machine that might actually power. It's called the demo machine. So this guy was explaining, and he was putting his time scale on it, and then people say, well, wait a minute, you're starting constructing before you get any data from ITER. Should you wait to see if ITER worked before? And he said, yeah, we will start building it before ITER put any result. So you just said that, yes. So those guys, they're going to go for it. But they are going the big monster ITER route. They are not very imaginative on new stuff. China tends to be good at taking some technology and making it, but they're not so innovative. So we're trying to sell our little special type of fusion, and we're not getting much traction in China, unfortunately. Too bad, because they really need it. But they're putting huge amount of resources, and they're going to make the machine after ITER, before ITER type thing.
Well, actually, can I amplify that a little bit? And
sure.
It actually distresses me a little bit for the U.S. home team, because this is actually broad spectrum. It's not only fusion that China's heavily invested in, it's in the broader spectrum of fission as well.
Yes.
And globally, they're just massively more committed than just about anybody else.
So the question was talking about shiny objects. So Tri Alpha just went through a rebranding of TAE. How do you, as you rebrand, keep the focus and what is the rebranding?
Yeah. So formerly Tri Alpha Energy, now Tae Technologies, because like the space program, along the way we've generated a large amount of IP, and some of that is relevant to other fields. But we're trying to do it in a way, and this is a little bit of a preview of coming attractions. I mean, this is a new thing. But we're trying to do it in a way that does not extract from the core mission. Like I said, I'm director of physics. This has not touched me yet. This has not touched the core physics team. If I, and probably Ray, have anything to do about it, never will. So it's,
it's a good
separate
answer,
companies.
Matt. That's a good answer.
Separate companies, subsidiaries, for example, that might now take stuff we have developed and try to commercialize. But that's we're a commercial company. So we view it as a natural part of the progression.
Got a very enthusiastic person.
What do you think the potential of generating fusion inside nanotubes is?
Potential of generating fusion inside of nanotubes.
No idea. Like, how would that work? Like nanotubes, fusion? No, I come in blank. I don't understand.
Right.
Do anybody have an idea?
Well, I would just say that there's a difference between getting fusion. We get fusion every day. We produce some fusion reactions. But getting net energy out of fusion is a completely different ballgame.
Yeah. Key point.
So I'm going to go Michel and then that person.
How is artificial intelligence accelerating fusion?
How is artificial intelligence accelerating fusion?
Oh, artificial intelligence, that's a cool thing to say nowadays, so everybody have to put a bit of AI in their stuff. So we have our Microsoft people trying to put a bit of AI on our thing. I think it'll help a little bit. I don't think it's like super magic, essentially. It'll help us looking at our data a little bit more efficiently. Like every time we shoot, we have a big reel of data, we put it in a hard drive somebody, and we probably have our physicists looking at 25% of the data on the hard drive. And 75% of the hard drive data, nobody ever look at it. So at least those automatic machine will look at this data. It might help to learn tricks a little faster. I don't think that for us, a general fusion will be a big game changer. It might speed things up by 7.2%.
Well, I'm not going to put a 7.2% on it.
Plus or minus.
Right. But yeah, so we, as some of you may know, we're working with Google. We recently came out with a paper of them about something we're calling the optometrist algorithm. Optometrist in the sense that when you go into the eye doctor, they go, do you like one better or two better? And this is really a machine learning enhanced design of experiment platform, essentially. So it's helping the operators of the machine optimize the machine faster. So I view the machine learning as speed, uncovering things in the data that you didn't have people to look at, and in that sense, doing more than you used to be able to do with the same team size.
Imagine 40,000 shots, 10,000 variables. Human beings digging through that. It's not possible. That's what machine learning is all about.
So I think the question is, in a world where we're moving to more distributed generation, or that's one of the models that's coming up, how does fusion fit into that picture?
Well, we want to make a machine in the sort of 200 megawatt range, so we don't want to make the multi-gigawatt machine. So in place of being a big plant in the boonies with a big power line coming to the town, we would rather like to put one maybe at each substation type thing, like 200 megawatt per substation connected on the grid. It's not at the house level for sure. That's not gonna, you can't produce a 10 kilowatt fusion machine, that's too hot. Usually those things scale bigger, better actually. So it's a little bit smaller than the normal big gigawatt machine, but it's still fairly much a grid-oriented thing, not a home thing. For us, anyway. That's what we want to build.
I would add that it's not a science problem at that point. If we can pick what we think is an economic location, but it's almost an economicist regulatory problem, NIMBY issue. Does anyone actually say one of us produces a safe small reactor that could power a town of 100,000 people? Will anybody believe that it's safe to put one in? So there's an education aspect to it. There's a lot that goes in that's just not science and engineering, and I don't know that anyone up here is the expert in that.
I would just add that part of our thinking in trying to go straight to the aneutronic fuel cycle is to try to go to the point where NIMBYism is minimized. So it would be the scenario with the least hazard, so you could expect the most ability to site these near cities distributed.
At the end of the day, it's going to be the cents per kilowatt hour that will talk. If the cost of producing electricity at X scale is cheaper than Y scale, then it's going to be done at X scale. That's the final word.
If you're producing electricity, if you're using it for something else, like
powering
cargo ships, and even potentially moving oil around the world in the transition economy, say, that's a performance measure. So different application, maybe a different regulatory framework. Power might not be the first application.
Good point.
Blue shirt. Yeah. So the end objective of ITER is to get above break even and to do some plasma physics studies. And DEMO is to be the first power producing plant of that type. What are the end objectives of your technologies?
Well, it was also a bit of a question about pulse versus DC, if I understand correctly. ITER is a DC machine, and those guys are DC, we're pulse. We want to make pulse, so we would like to make a pulse at 1 Hertz repetition rate. Each pulse would produce 100 gigajoule of thermal heat per shot. And because of recycling power and the 30% efficiency of Carnot efficiency, we'll cut out about 200 megawatt, but DC, because the machine will go pulse, but the inertia of the heat machine, like the thermal capacity of the liquid metal and the steam generator, that will spin continuously. So the turbine will spin DC, even if the fusion will be done 1 shot per shot. This is our end goal at General Fusion. The other guy can talk about their scheme.
Well, that was accurate. Yeah, instead of a pulse scheme, we're pursuing a steady state machine so that it would be continuous. The plasma would endure continuously and continuously generate energy.
And then the only thing I would add is we also have a steady state machine. But one of the things that makes us excited about our particular configuration is it has the potential to be in an ignited mode where we don't have to recuperate power back in. If it can operate almost like a campfire where you add fuel, but you don't have to keep blowing on it. And that's a promise. Well, whether we'll actually get there or not will depend on how the physics plays out. But the promise for that's there, and that's one of the reasons we're excited about it.
Yeah.
So the question is, once these are producing electricity, and if an emergency happens, how easy are they to shut off? What happens in an emergency scenario? And so we'll go in this order.
So you have some energy stored in your plasma. I think for most of our, well, at least for the steady concepts, you're talking megajoules. So you do have sticks of dynamite worth of energy, but you can control it fairly quickly. You can taper that off over a few seconds. And you also have energy stored in really high magnetic fields. So those are your main two sources, and we can engineer safe shutdowns. But you're talking on the order of seconds to dissipate that energy. So it's a solvable engineering problem, is the short version.
Well, I'll answer that a little more broadly. And the bad thing about having to make a thermos bottle for plasma that's harder than the center of the temperature sun is that it's hard, and the good thing is that it's really easy to shut off because it was hard to make in the first place. So there's no way for this to get away from you as a fission reactor might. And then just to bring it back to fuel cycle again, one of the reasons we feel motivated to go to the proton boron 11 fuel cycle is the fuel's not radioactive, the ash is not radioactive, so there's a very low prospect for any kind of release of anything hazardous.
Yeah, fusion is very hard to get going, so if something goes wrong, it just flame out, and there's no after heat. Like on a fission reactor, when you turn off the reaction, it's keep producing, I don't know what, 30% of the energy or something?
7%.
7%? Anyway, it's a fairly large amount of megawatt of heat produced by the radioactive decay of the thing. So you have to keep cooling with a pump. And that is no problem. With fusion, you stop it, there's no more heat, it's gone. So it's much safer for that sort of reason.
Go ahead, sorry. Yeah.
The question
is, you have to wait for the question.
The question was, so electricity is highly commoditized. If you're spending all this money making these machines, what is the real commercial prospect there?
It's a great question. In fact, I think a lot of venture capitalists who got into the energy business in the 2000s forgot that energy is a commodity, and whether it's also water and everything else is a commodity. Oil is a commodity. So you have to think about way downstream. The first of a kind plant, it's not going to be economical. Sort of the national price of electricity is about 12 cents. There are places in the world where Japan, where electricity is 40 cents. So how you build it and what the ultimate economics will depend on where you go with it. Obviously, you're not going to put a 20-cent electricity plant in an area where you can make electricity for 3 cents. So, you know, people today talk about shale gas as sort of the standard, but I remember when shale gas was $12 a million. So it's it varies with area and it varies with the ultimate technology, but it's a long ball. The first plant's going to be very expensive, maybe 50 cents or $1, but it'll come down over time. Solar, right? I mean, this was a huge deal in the last decades, come from like $5 down to less than $1. It can happen. So we have to have a long-term perspective in order to get it there.
And it does have a promise. The physics scales, so if it gets to work, you look at what the material costs scale out.
Yeah.
We see that, you know, first, second, third generation plant eventually becoming cheaper than what we pay now. And then it opens up. I love water as an example, because if you can reduce the cost of power, suddenly desalination becomes economically viable.
Yeah.
And you know, you look at what's the value of energy. It's not just like energy, it's what you use it for. It's for growing food, it's for cleaning water, it's for a million other things.
Powering ships.
I'll amplify a little of that because it comes to a question I get all the time, which is people say, okay, well, wind and solar power is cheap now. Why are you wasting your time? To which I usually answer, yes, if you use it right away, but stored solar and wind power is not cheap at all. So that's potentially the market we're trying to address, is base load, 24/7 availability, carbon-free.
The question was about core fusion and how that quark fusion and how that changes the game.
Quark fusion will not make energy. Like, in order to get the free quark, you need a super duper super accelerator. Costs you a gazillion GeV to make one quark. Then you make your quark fusion and you produce a few GeV, so you'll never pay back for the accelerator on the backside.
There you go.
No disagreement.
A lot of zeros there, I think.
So solar won't be cheap on Mars and increasingly far from the sun. What are the other potential space or propulsion applications?
Sure, fusion can do propulsion.
So you're a man after my own heart, and I do recognize when you see a picture of our machine, it's a nice long tube, and there's a core in the center, and plasma flows out either end. So you chop one end off, that looks an awful lot like a rocket.
And one thing I would add, I mentioned different applications. So space, very different application, different engineering constraints. You put different constraints on a problem, you get a different answer. One of the biggest challenges with the first generation system is those neutrons and making things activated and shielding. Besides making the fuel you need in a breeding situation, you're also, part of that shielding is keeping people safe. So if you're out in space, and say we're doing robot cargo missions to Mars, maybe you don't need so much shielding. Maybe that's a lot lower cost. And so it opens a different problem, different solution. That's where you get some innovation happening.
I have two fun little facts about this. Fact number one, Jeff Bezos invested in my company. And when I talk to him, I say, okay, why are you doing that? And the guy is a rocket nerd, actually. He's got his own rocket company called Blue Origin. And he invests in my company in order to develop fusion, because he thinks that eventually fusion will be good for space travel, which is funny, because I think it's more important to make energy. But anyway, I do take cash. And the second thing, there's a guy in the fusion business called Glen. He's been selling fusion for making energy for a huge amount of time and didn't get much traction. So nowadays, trying to sell fusion for planetary defense to shoot down an asteroid that might destroy our planet. Because he said, if an asteroid comes back, you will have to get there very fast. You can't get that with normal propulsion. So fusion is the only way we can protect the planet from asteroid. And he's trying to sell that in place of selling energy. So, so you go.
We have time for what? Yeah, we have not enough skill sets in certain areas. So when we get to a place where there's more fusion in the world, what are the skills that we should be developing? What are the gaps going to be?
Pick me. So in the last 30 years, the supply chain for building fission plants has really gone away quite seriously. And so we are short-skilled on building these things. However, the fusion plants don't have the same requirements as fission plants from a construction and safety point of view, so it may be different. I think actually it's the operational side. There's a whole new skill set. And there's a lot of software here, there's robots here, there's all kinds of chemistry. If you think about cleaning out one of these machines or doing the replacement, I think there's stuff we don't even do now anywhere. We will be doing it in the fission. So I think there's going to be a lot, if it's not all robotics. So I think building robots to do the nasty.
There's highly,
you know what I mean. Okay. Well, they're laughing over there.
I would add, there's highly specialized fields where you go get a PhD to do. And then there's a lot of really important jobs that you don't need a PhD to do, that we don't train for now. For example, where we work out at the Skunk Works in the desert north of Los Angeles, there's a bit of a boom now with new programs coming in and ramping up of hiring. And a lot of those positions are ones that you can get with a crash course technical program in a number of months and then get hired on and do some highly technical work. I have folks on the team that are building airplanes for 30 years. And you think, well, how does building airplanes tie into trying to do putting a stun in a box? Well, it turns out cross-discipline, combining mechanical design, thinking outside the box, electrical controls, various like advanced computing, putting it all together. You get smart people that are used to solving hard problems. You know, you have the base for what you need to do, and some of that's just job training. And I don't think we know exactly what that job training is going to look like operationally. Yeah. They don't all have to be PhD plasma physicists, but we'll probably need quite a few of those as well.
In fact, I'll mention that the PhD plasma physicist is one of the easiest things to hire, believe it or not, because we generate a lot of them, and because of some troubles in the larger programs, they don't always have somewhere to go. But I think to answer your point, it's sort of the broader STEM base that we need, because honestly, one of the reasons I believe strongly that we're on the approach to commercialization is we're using more and more commercial technology. You know, we use field programmable gate arrays off the shelf. We use control systems off the shelf. And the things we compete with the most are people with skills in that sort of thing, programming, control systems, embedded system design, because we're competing with other people for them, very strong industries.
I just wanted to put a question in that was texted in. You talked about storage being less of a problem with nuclear fusion as opposed to solar and wind. Can you explain how storage is easier with nuclear fusion?
Well, you don't have to store anything, right? So the fusion power plant would then allow you to put energy into the grid on demand 24/7, and it would alleviate some of the need to store large amounts of wind and solar.
You make it when you need it. When the sun shines, you have to store it if you don't need it at that moment. That's what he's referring to.
I'm sorry.
That's all right. I think that's what you meant. Mm-hmm. Same thing with any sort of naturally derived wind or solar. You have to store it if you can't use it immediately. But a coal plant, a gas plant, a nuclear plant, you can fire it up and hold it and turn it down.
Moderator's prerogative. What's the ramping capability of fusion plants in terms of power up rate or down rate to respond to grid demand? Has anybody looked at?
You get that question quite a bit from utilities, and they're like, well, what's it look like and what's compared to what we already have? You might be able to get the confinement time scale for a plasma in our situation. Plasma behaves at different, whether it's really, really dense or a little more diffuse at different temperatures. But in our regime, it's a few seconds is what you're looking at. And that you go from cold to 200 million degrees hotter than the sun in a few seconds. The bigger question is, what's your energy conversion cycle? So if you have this hot blanket that has a thermal inertia to it, that you have to heat it up, I think that's more of an unknown. And whether that is a minute or 20 minutes, that probably depends on what's the fastest you can safely bring that up. And that becomes a thermomechanical problem that we haven't looked at in that amount of detail. And that might be different for different concepts.
Yep. In fission, there's a concept called hot standby, right? Mm-hmm. So, yeah.
Okay. We're a pulse machine, so we can change the pulse rate. Mm-hmm. So each pulse will be exactly the same, but we can go at full bore, or we can pulse less and less. It's a bit like your car, the RPM can change to adjust to the load. So we can run at half power, or at a quarter power, or 10% power, or we can suddenly run at 100%, and we can follow the load, so which is advantageous for a pulse device.
Great. And I realize I don't know what time I'm supposed to be finished.
Last question.
Okay, great. So you each have different designs. For each of you, what is the biggest hurdle you're facing now? And it can be scientific, or it can be managerial or financial, whatever it is.
Raising money is always a big deal. That's a big hurdle. And after that is battling with the machine. Like, I'm supposed to be a PhD in physics, but basically I'm a glorified plumber and electrician. I patch leak and I fix broken circuit board. And when you build those machines, you battle the equipment, and that's pretty standard.
I'll have a little more specific of an answer for you. So with the new machine, you saw some images of. We call it Norman in honor of our founder. We're on a very specific year and a half mission to see how that thermos bottle scales with temperature. We have a theoretical expectation that says one day we could get to an advanced fuel cycle, but we have a milestone, money by milestone, to check that at a multiple of 2 to 3 of the temperature we're at now.
We're in a similar situation. We've got an experiment that's where we want to have results by the end of next year, and what those results have bearing on moving on to that next milestone or not. And on top of that, there's a lot of different threads. We've got some parallel development. We're working on superconducting coils and supercomputing and magnetic shielding of some components in parallel. So part of the challenge is really prioritizing and distributing resources. So what's the right balance to get to you want to hit your milestone, but you don't want to sacrifice everything in the future, because we don't want to have a big pause. We don't want to get there and have to wait for a year because we forgot to do this one part, and it's going to take a year to do that part. So it's sort of a constant motion problem where it's sort of like chess. You need to not mess anything up, but you still also have to have a good strategy to win, and it's trying to balance both of those things.
And I'll just finish with the raising money, but not just raising money. Mother Nature tends to throw things at you don't expect, and it's not a straight walk to success. So you need to plan for a couple of bumps along the way. And if you start to run out of money and you haven't got to that milestone, that's when raising money is really hard. And you need to have a syndicate around the table who believes, trusts, and will write the next check. Because raising it from new people isn't going to come very easily. That's it. Okay. Good job, guys. That was great.